In section 6.3, we introduce and discuss the notion of joint typicality. Here is the setup. Consider a bivariate random process x sub k, y sub k, where k is bigger than or equal to 1, and x sub k, y sub k is a pair of IID random variables with generic joint distribution pxy. Let the pair of random variables x and y denotes the pair of generic random variable with finite joint entropy. We also assume that the alphabet x and the alphabet y are both finite. Here are some notations. Consider a pair of sequences x and y of length n. Let n x, y, semicolon, sequence x, sequence y be the number of occurrences of the pair of values x, y in the pair of sequences x and y. Dividing this by n, it becomes the relative frequency of the pair of values x and y in the pair of sequences x and y. The collection of relative frequencies is called the empirical distribution of the pair of sequences x and y. Here is an example. Let x be the sequence 0, 0, 1, 0, 1, 1, and y be the sequence 0, 1, 0, 1, 1, 0. Then the number of occurrences of 0, 0 is equal to 1. The number of occurrences of 0, 1 is equal to 2. The number of occurrences of 1, 0 is equal to 2. And the number of occurrences of 1, 1 is equal to 1. In definition 6.6, we define the strongly jointly typical set. The jointly strongly typical set T sub xy delta sub n with respect to the generic distribution pxy is a set of pair of sequences x and y such that the number of occurrences of xy is equal to 0 for xy not in the support of x and y. And summation x, summation y, the absolute difference between the relative frequency of xy and the true probability of xy is less than or equal to delta, where delta is an arbitrarily small positive real number. A pair of sequences xy is called strongly jointly delta typical if it is in T xy delta sub n. Theorem 6.7 is a property called consistency. It says that if a pair of sequences x and y are jointly delta typical, then x It says that if a pair of sequences x, y is jointly typical with respect to pxy, then x is typical with respect to the marginal px, and y is typical with respect to the marginal py. Theorem 6.8 is called the preservation property. Consider a random variable x and let y be f of x. If a sequence x given by x1, x2 up to xn is delta typical with respect to the distribution px, then the sequence fx obtained by applying the function f to the sequence x component-wise is delta typical with respect to the marginal distribution py. The proof of these two theorems are rather straightforward. For the details, please see the textbook. Theorem 6.9 is the definition for strong joint AEP. Consider a pair of random sequences xy whose components are x1, y1, x2, y2, all the way to xn, yn, where xi, yi are IID with generic pair of random variables xy. Then there exists lambda greater than 0, such that lambda tends to 0 as delta tends to 0, and the following hold. First, if a pair of sequences x and y are jointly delta typical, then the joint probability of x and y is lower bounded by 2 to the power minus n times the joint entropy of x and y plus lambda, and is upper bounded by 2 to the power minus n times the joint entropy of x and y minus lambda. For n sufficiently large, the probability of the pair of random sequences x and y is jointly delta typical is greater than 1 minus delta. And third, for n sufficiently large, the size of the jointly delta typical set is lower bounded by 1 minus delta times 2 to the power n times the joint entropy of xy minus delta, and upper bounded by 2 to the power n times the joint entropy of x and y plus lambda. The proof of the strong joint AEP is exactly the same as the proof of the joint AEP, so it is omitted. Let us now discuss a very fundamental tool called Stirling's approximation. In Lemma 6.11, we present a simplified version of it, which says that for large n, the natural log of n factorial is approximately equal to n times log n. The proof goes as follows. First, we write log n factorial as log 1 plus log 2 plus all the way to log n. Since log x is monotonically increasing, we have the following bounds for the kth term above, namely log k is lower bounded by the integral of log x dx from x equals minus 1 to k, and upper bounded by the integral of log x dx from x equals k to k plus 1. These bounds on log k can be visualized graphically. For the lower bound, we see that it is valid because log k is the area of the green bar. Obviously, it is lower bounded by the integral of log x dx for x from k minus 1 to k. For the upper bound, it is seen to be valid because log k, which is the area of the red bar, is obviously upper bounded by the integral of log x dx for x from k to k plus 1. Now coming back to our proof, by summing these lower and upper bounds on log k for k equals 1 up to n, we have log of n factorial lower bounded by the integral of log x dx from x equals 0 to n, and upper bounded by the integral of log x dx from x equals 1 up to n plus 1. Upon evaluating the integrals, we have log n factorial lower bounded by n log n minus n, and upper bounded by n plus 1 log n plus 1 minus n. Note that we have n log n in the lower bound and n plus 1 log n plus 1 in the upper bound. These terms are much bigger than n when n is large. And so, for large n, we can approximate log n factorial by n times log n. Let us now discuss a very useful approximation for the binomial coefficient, which says that for large n choose np, which is written as np, n1 minus p, is approximately equal to 2 to the power n times the entropy of the binary distribution p, 1 minus p, where the entropy is in bits. For the proof, consider the binary coefficient n choose np equals n factorial divided by np factorial times n times 1 minus p factorial. By taking the natural logarithm, we have log of n factorial minus log of np factorial minus log of n times 1 minus p factorial. We now use Stirling's approximation for each of these logarithms. First, log n factorial is approximated by n times log n. Log np factorial is approximated by np log np, and log n times 1 minus p factorial is approximated by n times 1 minus p log n times 1 minus p. Now write log np as log n plus log p, and log n times 1 minus p as log n plus log 1 minus p. Now observe that n log n, np log n with a minus sign, and n times 1 minus p times log n, also with a minus sign, cancel with each other. Upon factoring n in the remaining terms, we have n times minus p log p minus 1 minus p log 1 minus p. And this is seen to be the entropy of the binary distribution p1 minus p in the natural logarithm. Upon changing the base of the logarithm to 2, we have log 2 of the binary coefficient approximately equal to n times the entropy of the binary distribution p1 minus p in the base 2. And this proves the lemma. This approximation of the binary coefficient can be generalized to the multinomial coefficient. Let p1, p2 up to pm be a probability mass function. For large n, the multinomial coefficient n, np1, np2 up to npm, which is equal to n factorial divided by the product overall I, n times pi factorial, is approximately equal to 2 to the power n times the entropy of the distribution pi in the base 2. Again, we assume that np1, np2, etc. are all integers.